acceleration response first for the ATG model. And as I said, these motions were prescribed, which are common for everybody. So if I prescribe a displacement like that, the acceleration for our shaker came something like this. And we were asked to do 0.25 G, and we can't. We ended up getting 0.276 G, which is close enough. But as I said, a few of our instruments did not work. That one did not work. Initially, I thought that also did not work, but actually, it turns out there's quite a bit of dilation going on the top, so it could be trying to tell us something. But these two certainly work, and you can see that every half cycle or so is trying to, the soil is stopping from moving. That's why we're getting big acceleration spikes, which we looked at yesterday. The new marketing explains all that quite well. We also looked at the frequency response of the input motion. So most of our energy should be at 1 hertz, which at prototype scale, which is, and we have a component at 3 hertz. Most of these shakers have a 3rd hertz component. That's just the mechanical resonance in the system. Okay. Then let's compare the accelerations at 1 G for the other test, which where we're using doing the test at 1 G. Now, same input motion we prescribed, but if you, I'm going to show this. Yeah. So initially we applied the same 0.2 G or something like that, and okay, we were getting massive amplification. If you see the peak here, it's gone up to 0.38. However, the slope did not move. I'll come to the movements later on, but the slope absolutely did not move. So we said, right, this is not working. Let's try and apply a bigger earthquake. So we kept doing, we got 2 arrays now, so that we know the left array and the right array in the same soil, and so we can be very sure of the consistency of the model. So if you got 2 sets of columns and instruments at the same height are saying the same acceleration, then we know the model is right, the instrument calibration is right, everybody is happy. And at 1 G, again, this is the FFT of the input motion. So once you scale, it's 1 hertz and 3 hertz components. But for this, you can see the 3 hertz component is bigger. There's nothing I can do about it. It's just the way the shaker works. Then we said, in order to make this slope move, we hit it with a secondary earthquake, which is 0.25 or 0.3 G. It still did not move. Then we hit it with the 3rd, 4th, and 5th earthquakes, increasing the strength. I'm going to show you the results of this 3rd earthquake, because here we are applying an input motion of about 0.5 G, and the peak acceleration recorded at the top of the slope is 0.97 G. It's almost 1 G horizontal. And what does that tell you? That tells you that the soil at the surface, being under only 1 G condition, is going to be extremely dilated. It has no stress, so every grain can rise up as it wants to when you try to shear it. So your soil is going to behave in a very dilated fashion and lock up on you. Therefore, the accelerations can become really, really big. In theory, this number, because I'm using the same scaling laws, should be the same for this slope as the other one. But in the other case, we put 0.27, we got 0.38. This one we put 0.5, and we're getting nearly 1. And if I put 0.25, nothing happens. So the slope does not move. Clearly, you're starting to see the differences between the 2 models. Now everything has been scaled to prototype using the scaling laws I earlier showed you. So we are following EIE. This fluid viscosity has been scaled according to his rule. We scale the earthquake motion according to his rules, and we are playing the game we are supposed to be playing with those scaling laws. And the right area also confirms fairly large accelerations. Now let's look at the excess pore pressure. So the accelerations are not quite matched. Excess pore pressures, for the first one, they are building up like so. And I mean, basically, that's the input motion, and you're going from base, middle, uh, bottom third, middle third to top third. So you're going vertically upwards. Of course, whenever you do this PPT didn't work, you'll always have some instrument failures. But you can see for this type of smiley face motion, the pore pressures take a little while because the motions are small here to build up. They get to this full liquefaction level and then they stay, and you get these suction spikes, okay, which is consistent all through. So that I'm showing during the shaking for 0 to 20 seconds. If I plot long term up to say 450 seconds or something, then you can see how long the pore pressures are taking to dissipate. So this the base one starts to dissipate first because all the fluid is trying to go up, and this fluid coming from below keeps this liquefied longer and even longer at the surface. So physically, it's all consistent. Right. Let's look at the pore pressures for the other one, for 1G. So these are because we scale the pore pressure using his scaling law, the numbers look reasonably okay. If you see the top one, that's about 13.2 kPa. This was about 11. That seems scaling law for the pressure is working all right. And similarly, these numbers, although the absolute pressures we measured were much smaller, the pore pressure scaling law makes them look reasonably comparable. So that part of EIE scaling seems to work okay. Okay. However, if I do the long-term plot, just like I did for the previous one, to see how long it will take for the fluid to dissipate, you can see that's dissipated within maybe 50 seconds, it's all gone. Whereas this one took nearly 300-400 seconds. So although the pressure magnitude is being scaled properly, the time of our dissipation is not being scaled properly. And this is the problem, which means that the pore pressure builds up, and we think, okay, but before the slope can move, the pressures are gone. And that's why the slope wasn't moving when we were hitting with this the right size earthquake. We had to hit it harder and harder. And you could confirm this for the central, the other area as well. As I said, doing the CPT was compulsory for both. So we said, right, we're going to do the CPT at 80G and 1G and see how the strength actually compares from these. So we've done the CPT. Uh, we do this twice, before any earthquake is fired and after the earthquake is fired. Now, they're reasonably consistent. The slope is only 4 meters steep, but we can't go all the way to the base. Mostly because we're scared we'll drive our CPT into the base, in which case we'll destroy it. So we stop about half a meter in terms of prototype scale of the base. Now, you can see it's quite consistent increase with that. There are a little bit of unevenness for various reasons of model making, where you stop to put the instrument. When you start it again, the machine may pour a little bit of a loose layer or something like that. But we know what it is and where it is. That's the good thing of doing in-flight simulation. 2 points. Let's keep an eye on this 4 megapascal. Uh, Actually, yeah, better than that. Let's see at mid depth of the slope, 2 meters, what is the cone resistance. So the cone resistance is about 2 megapascals. Keep that in your mind. Yeah. So this is for the ATG test. When we do the same test at 1G, oh, sorry. Oh, my apologies. Uh, no, this is the actual measured value. Okay. Now, because it's a cone tip resistance is a stress, we, according to what we are trying to do here, we need to use the scaling law for stress to scale this x-axis, right? So if you do that for this set of ATG and mu of half, my resistance drops to at 2 meter depth to about 1 megapascal. So that's just once I use EIE scaling law to scale this. Okay. Now let's look at the 1G test, where we push the CPT, the raw readings say that we got hardly any cone tip resistance. It's about at 2 meters, about 0.05 megapascals. In other words, I got about 50 kilopascals. What do you expect? I got soil this deep and I'm pushing CPT. Of course, it's not going to give me much resistance. That is completely understandable. What I'm going to do now is to scale this axis using EIA scaling law, just like the other one. That's what it does with it. It's now made it jump from being almost no strength to that. Again, green is, black is before, blue is after. If I take the 2 meter depth level, I can say it's coming up to about 1.5 megapascals, or a bit more than 1.5 megapascals. So when I scale it from in my ATG test, the scaling law made it go from whatever the higher strength I had to 1 megapascal. For 1G test, it's pushing the other way and pushing it way further, which means that something, well, the scaling law we are using for stress is not right. Agree? It pushes the things in the wrong direction. But as I said before, the scaling law for pore pressure works better, at least in the magnitude sense. And this is the problem. You tie yourself in knots because stress and strength in this case all have the same units. Therefore, they must all scale the same way. But they don't. We derived those earlier, and each had its own set of scaling laws. And if I'm using those scaling laws appropriately for those things, some are getting pushed further, some are not going as far as they should. Okay? So it's not just saying things don't work. We have looked at this carefully and see which parts of the scaling laws are actually salvageable and which are not. Now, of course, the whole purpose of this expert LEAP project is to establish soil deformation. Slope deformation is the problem. The others are all for us to have fun, for numerical models to compare and so on. So deformations is the real engineering parameter. And we do this using our high-speed camera, and you get images like this. And this is before the earthquake, And I'll show you one after. You can see if I play back and forth, what the slope is doing. Keep your eye on this slope. You can see how it moves. Exactly as I said, the whole thing basically did that, right? So, yes, we got the digital images for that. Because we got digital images, you can then track the particles and plot the displacement vectors, which look something like this. So the vectorial displacements, this bit goes down and the middle bit goes horizontally and these bits come up if you plot this carefully. And you can separate out the vertical and horizontal components of these and use nice MATLAB contour plots to show which bit is going down. Obviously, upslope is going down, and this bit is going up. Horizontally, that bit is moving most by less compared to this bit. Okay, so this is all cool and neat for the ATG test. So we're looking at displacements in terms of centimeters here, so 50 millimeters or so, right, at prototype. Also, what PIV allows you to do is to pick certain points. So I picked A, B, C along the slope and D at some depth. So for those particular ones, I can get the time traces. You don't need LVDTs to measure displacement. You basically follow where these points are moving throughout your earthquake, which gives me displacements. So I can use just that information I showed you earlier as a time trace and see A, horizontal displacements, A moved least, B moved most, and others fall in between for those 4 locations I have shown. Also, because we can track the dots on my box, I can get the displacement of the whole box. How much is it moving by? And that confirms that the motion we imparted is exactly what we wanted. So you don't need displacements. The input motion we measure acceleration, but we can also get the displacement of the base directly without integrating. Vertically, the point A, which is on the upslope, settles most. B and C settle less. But interestingly, point B heaves. It's going the other way. And that makes sense because if my point A, B, C, and D, if it's doing this way, this point can go up, right? Yeah, no. The color. Keep the light blue is D, yellow is B, C is this one. The colors are slight. Sorry, I should have chosen better colors. This is Excel. I apologize. It can't possibly do anything. It's getting this information from the picture, so there's no way it'll get that wrong. Now let's have a look at this 1G test we did. Same process, exactly the same process we followed. Only one thing is, I'm going to say, is for earthquake 1 and 2, as hard as we looked at them, there was no movement. That's why we were firing bigger and bigger earthquakes. So the only time we got some movement is when we were applying this 0.5G shape, much double than what was prescribed by the LEAP project. Now, even then, with double the input compared to the other ones, it did that. Okay? Hardly any movement like what we have seen. And if I now plot the displacement vectors where we are getting nice big things before, you can hardly see the bloody displacement. It's not going anywhere. That's the problem. It's too stiff. So if you do the test at 1G, the soil is too stiff. And therefore the deformations will be small. this scale, although you can pick this up, we barely, we barely trust it ourselves. It is within the limits of our measurement using the cameras. That's it. You can see some pattern that, right, there is some movement up here of about half a millimeter, maybe close to zero here. Blue is the bottom end is zero. And so that's the horizontal resultant contours, vertical and horizontal. None of them you can trust too much. It's within the accuracy limits. But because we got the movements, if I try to track this A, B, C, and D again for this exactly same equivalent points in this new slope, you can see the displacements even scaled are 0.02 meters, which is 20 millimeters, yeah, or 2 centimeters. Yeah, hardly moved. And just to check that we got the measurement right, we are tracking our input motion again, and that comes out fine. So there's nothing wrong with our system of measurement. And vertical settlements, similarly, you can't really tell whether one is settling more than the other. That's the problem. So, in summary, what have we done here? Okay, in high headline terms, we've done tests at 80G and 1G as part of the LEAP project, and we played the game according to the rules set by the generalized scaling clause. Now, clearly, acceleration spikes at 1G are much larger than at 80G. Excess pore pressure magnitudes reasonable. That's the one bit of positive news we got. However, the rates of dissipation are wrong, which means the dissipation times are not scaling the way you think they should. Displacements are almost unobservable even when we are hitting with twice the prescribed earthquake. And this was confirmed both visual inspection as well as the PID. So I've shown you both. So we can click through the images or get the computer to track the displacements. Both of us are failing miserably because to start with, the displacements are so small. Now, having said all that, what do you guys think? Is that enough proof that if you use these scaling laws, what you do not want to do is to go that step I was talking about. Don't ever try to go up. And all the results I have shown are completely consistent with soil basically being a lot stiffer and a lot more dilatant at 1G compared to at higher Gs or in the prototype. So you're trying to take a material whose fundamental property is to have a stress dependent response in terms of stiffness and trying to meddle with its the way it behaves. And you can't do that because it won't behave the same way as it will do what it wants to do. So my advice is by the way, if anybody wants to have a go at doing a numerical analysis of this, you can have a go. And but before you do, I suggest you look at all the papers that have been published. A lot of work on this has been published. So it's good for you to rerun and check that whatever code you're using is actually able to predict the properly. So that's a good verification exercise. But I wouldn't term that as fundamental research anymore because there are lots of other people, unless you write your own code, of course. But if you're running this using FLAC or galaxies. A lot of other guys have done that already. So that's not quite uh, original research anymore. But for those of you who are doing, oh, we're doing small scale testing, what is our Panacea? What I suggest is that do this. So this is my 1G small scale model. So it's effectively you got your mu factor and your eta is always going to be 1 because you cannot change the G. So given that lambda is a multiple of these two, either you be brave and say, right, I'm going to try and have a go at doing start from the triaxial test data, try to normalize that and see whether you can normalize it a bit better than what EIA could do for the Toyota side. Or if your time is limited and it's a master's project, try and compare different versions of these. These are all physical realities. So these can be compared. Multiple tests with variations can be compared with one another. There's no problem. The only problem comes when you are doing this jump to full scale using the laptop. And that's the best you can do with the material we got. Okay? But bringing back into what this course was about in terms of, say, the pile foundations and how would we model those, investigate whether you can change the relative stiffness of the pile with respect to the soil. Maybe use plastic piles or paper piles or whatever the EI you want. There are other materials which are much softer. Don't stick in an aluminum pile because somebody else has. That's not a use your innovation if you like, and try and come up with other ways to have a good idea of what is the problem, what is the main issue or main problem you're studying. If it is to do with, say, dynamic sources interaction between pile and the soil, by all means, then you know the important thing you should get right is the relative stiffness between the pile and the soil. Get that right, even in a 1G. Then you can compare with several 1G tests. As long as you then don't say that, oh, the Kobe piles are going to behave this way, in reality, everybody's happy. And that's useful contribution as well, as I see it. It's just overreaching to the far right is the problem. Any questions? Yeah? We have tests, the ones I was showing you yesterday with 6 degree slope also. Those are all done in laminar box, and you get a lot more lateral spread. And actually, the mechanism will be right. In this case, we are picking up the failure mechanism as a rotational mechanism, which is not how lateral spreading happens. Lateral spreading happens more like a downward movement of the entire body, and that is captured by the laminar box. And I showed you the displacement of the slope when we like, like that. Whereas here, for the lead project, the displacement profiles are, it may be a bit like that there, but it's different here and different here. Because we're doing that. Yeah, but those kind of tests we have done before. At the moment, we're working on making a laminar box, but with a perspex front. So we want to combine our ability to do the lateral spreading, but with a view. Because this PIV business is too cute a tool not to use. And it really shows you where the soil is actually going. Because we can follow sub-pixel level accuracy with that, which means about a quarter or an eighth of the size of the sand grains, which is more accuracy than you normally need. But it does show you. We can actually back out the soil strains from it directly. So we can get volumetric strains and shear strains calculated from the displacement field. It's that good. And the guy who wrote the PIBB hired him as a new lecturer. So he's in our group. So it makes sense for us to keep investing in that. Any other question? So, what do you think of the scaling laws? At least we covered all the basics here, and you can go away and think about what is it that you're trying to do, and not just blindly use either Guy Holtzby's stuff on the scaling the density part or EIE stuff, because now you know the background for the whole thing, where it all started. So at least it's clear in your head. I hope. The teachers always assume that whatever I said has gone and imprinted in your brain, but I know it does. It does. Being a student before, I know that's not how it works. But if you remember at least the main headline points, that there is some issue with these things. If I want to know what the issues are, I need to do these things. I'll go back and read a paper or whatever. You know, that's good enough for me. Right. I think I'm all done here, and I'm not going to set you anymore. I think you've overloaded with coursework already. So, hope is there an exam they have to take or something? You're saying
Yes, sir, in the afternoon.
afternoon. Okay. Good luck with that.
The question paper has been given, sir.
Already, yeah, that's fine. It's an open book, so it's
Answer
fine.
sheet will be given later. You please go through that in case you want. Your availability will come. 4 will be sent only through email. Okay, 4 will be on real science structure.